Hello, everyone. Thank you for giving me a chance to speak here. And I'm Masaru Dobashi from NTT Data Japan. Today, I will talk about Spark on Yarn and its evaluation from the viewpoint of enterprise Hadoop user and a developer. And I'm a chief engineer of NTT Data in Japan. And NTT Data is one of the leading solution provider in Japan. And my team focusing on open source software solutions. And I've been integrated several Hadoop clusters for over 5 years or 6 years. And one of the largest one is over 1,000 nodes clusters. And in these days, I'm also utilizing Spark and Star and so on. So I briefly introduce my company, and NTT Data is one of the NTT group, and NTT Data's net sales exceeds $13 billion, and there are 75,000 employees. And do you know NTT Docomo? You know, NTT Docomo is one of the leading mobile communications company, and Docomo is a sister company of us. Then we are addressing this Spark project with having a discussion with NTT Docomo. So, okay, today I will talk about our motivation and expectation for Spark. And next, I talk about characteristics of its performance with gigabytes and terabytes and tens of terabytes of data. And finally, I introduce you tips for people who are planning to use Spark. Then I talk about a motivation of us. So we started to use Hadoop maybe 6 years ago. The version was 0.9, so very old Hadoop. And actually, Hadoop enabled us to process massive data daily and hourly, and became the base of our data processing system. The image was the system of 6 years ago. And this is the example of massive data processing. And this is an NTT Docomo's project in Japan. And this project supports the research of society and industry using large-scale operational data. And in this system, Hadoop is used to process terabytes of data per day, and or 30 billion records per day. And produced data exceeds petabytes of data per 3 months. This is a success project, and but actually, recently, our demands for the data processing have diversified. The first, to handle a variety of requirements for data processing. Actually, we need both throughput and low latency, and also APIs useful for data analysis. We thought this should be achieved by Spark. And also, secondly, we want to make the data management more simple. We wanted to run different types of frameworks on one architecture which access one HDFS. This is because multi-clusters themselves impose the complexity and the inefficiency in data management. So we thought this should be achieved by Hadoop 2.x and also Yarn. So we started the evaluation about a Spark on Yarn. So this is a recent architecture image of massive data processing. In this model, the input data is gathered from the left side and passed through a messaging system, and the gathered data is processed right side of batch processing. The gathered data is processed by MapReduce, Hive, and Pig, and also, of course, Spark. The Spark assumes the role of on-memory rapid data processing, and this is a very important role for us. Okay, so today I will talk about the evaluation of the Spark on Yarn on the on-premise environment. So the most basic viewpoint is here, the above. To understand the basic characteristics about the scale-out, especially about tens of terabytes of data. The following is 4 important essential points we wanted to evaluate. The first one is the capability to process tens of data without unpredictable decrease of performance nor unexpected hold. This is evaluated by word count, a simple application. The second, the capability to keep reasonable performance when data is bigger than the total memory available for caching. This is also evaluated by a Spark HDFS LR or Logistic Regression Sample Application. And next, capability to keep reasonable performance of a shuffle process with the tens of terabytes of data. This is evaluated by group by test. You can large shuffle process test. And finally, easy to implement multi-stage jobs from our business use case. To evaluate this point, we started a PRC of a certain project with our customers. These basic applications we used are a little modified version of an official example of Spark. So you can find it from the source code of Spark. And this is the specification of a cluster we used. Total cluster size as here, the left side, and the total CPU core number exceeds 4,000, and the total memory size is 10 terabytes. And all servers are connected with a 10 gigabyte network. And we used the Spark 1.0.0 and HDFS and Yarn of CDH5. So let's start the result of execution. This is the result of test 1. This graph represents the process time or word count, and the horizontal line represents the input data size in terabyte, and the vertical line represents the elapsed time. We ran tests 2 times per each data size, and the OS buffer cache was cleared before each execution started. Almost the process time seemed to be linear per input data size, and in shown in right side, we found a reasonable performance even if all of data cannot be held on the memory. Then this is also the result, and a resource image of a usage of a certain slave node. This is a result of a test in which we used 27 terabytes data. And the first graph represents the CPU usage, and the second graph represents the network usage, and the third one is disk I/O usage. As shown in graph, because of locality of data, there are few network I/O. This is ideal situation, we think. And also, you can see in the disk I/O's graph, about 400 megabytes per second disk usage we found. This is very ideal for our hardware respec. Word count's performance depends on the mapper, and reduce might not be a bottleneck. Well, this is because mapper outputs small data. On this task, we confirmed a reasonable performance, even if the input data exceed the total memory amount. And fortunately, when task had a locality for data, we observed a stable throughput. But unfortunately, we found a case that the tasks lost locality, and I will talk about the case in which a task lost locality later. Then I will talk about a second test result. This is a process time of Spark HDFS RL. And the vertical line represents the theoretical input data size per server, per slave server, and the vertical line represents elapsed time. We ran logistic regression with 3 cycles for test. We found the ideal difference between the cycle. The difference of process time between cycle 1 and others seem to be depend on the cache data size. For example, in a test in which we used the 8 gigabyte data size, we find the cache is very effective because all of data are cached on the memory. And also, cache is very effective even if executor cannot hold all of data. And this is also the result, a resource usage of a certain slave node. And left side graph represents the result of the test in which we used 8 gigabyte data. And the right side represents a test in which we used 16 gigabyte input data. The first graph represents the CPU usage, and the second graph is the network usage, and the third one is disk I/O usage. As shown in the left side, the left side pattern, cache mechanism prevent the disk usage. So we found no disk I/O in second cycle and the third cycle. On the other hand, in the right side pattern, in which we used 16 gigabyte data, a part of data was on the cache. So we found a little disk usage and a little disk I/O weight of a CPU usage. The cache mechanism of Spark worked for iterative applications. And also, our DD's cache mechanism works consistently and enhances throughput, while the amount of input data is bigger than the total memory available for caching. But we found that it is very important to minimize boxing overhead when storing a data object into the cache. So this is a result of test 3, the process time of a group by test. The horizontal line represents the total shuffle data size in terabytes, and the vertical line is the elapsed time. In this test, mapper's output doesn't decrease compared with the mapper's input. So exchanging of large shuffle data should be occurred in the shuffle process. As shown in right side, we didn't find a drastic decrease of performance in these data size. And this is also a result of a test tree and represent the network usage of a certain slave node. And actually, the throughput seems to be restricted by disk I/O as well as network I/O. This is very typical. When we ran shuffle tests, whose mapper generated a large data. And the following is the network resource usage result of a certain slave node when we ran a variety of patterns of tests. The first one is a test in which we use small shuffle data on one rack, so that is why we don't have a network bottleneck of a course H. In this pattern, we found no spill out to disk, and also we found a very ideal network usage of slave node. And the second pattern represents the test in which we use large shuffle data, and we found in this pattern a spill to disk. In this test, we found that CPU util exceed 100% at this time, and the total throughput was restricted by the disk I/O. And the third pattern represents the test in which we use a large shuffle on a fault cluster. In this cluster, we have a weakness of a core switch bottleneck and also have a spill to disk. In this pattern, we found a more restricted performance of the throughput. So the process time seems to be linear per input size of data. When the shuffle data spills out to the disk access would compete among shuffle-related tasks, such as a shuffle map task and the fetcher and so on. Then, the competition deteriorates the performance. This should be, but recently, this situation may be improved by activities like Spark 2044. In this activity, many people are discussing about shuffle improvement. So soon, this will be improved, I think. And additionally, there are difficulties about Java heap tuning. Because executors have a variety of buffers and cache data in the same heap, the most unfortunately pattern, we met the auto memory error in the worst case. Then finally, I talk about a POC. This is the example application of POC. We categorized existing Hadoop applications in a certain project and made a mock applications, which represents major business logics of this project. And the middle line is the example process flow. This is a multi-stage job, which includes some computation different from each application. For example, we computed the difference between records. And after that, we computed the grouping, counting, and so on. This application resembles the log analysis to find a feature of web users' access. So we learned a lot of things from this POC, but today I will introduce you the two topics. The first one is to use cache mechanism efficiently, And the second one is to prevent scale-up task allocation in the start phase. First one is use cache mechanism efficiently. We can use the cache mechanism efficiently by minimizing objects stored in memory store or the data store of a cache mechanism. In other words, we'd better to use simple data format instead of a rich data format. And the convenience and efficiency of data size might have a trade-off relationship. But for example, an implicit conversion function of a Scala can help you in a certain case. For example, when you generate rich data format from simple data format in your own function, you can use implicit conversion and automatically transform the data format. It will be very useful. And secondly, to prevent scale-up task allocation in the start phase, we use yarn, so it takes a little time to start all of containers. When we run large jobs on a large yarn cluster, in this case, the task allocation starts before all containers are available, so that some tasks are allocated on non-data local executors. So that is why we executed our workaround. And the middle line is our workaround. We inserted a little sleep time. This reduced total processing time as a result. But this is a really workaround, I think. Ultimately, we should implement the threshold to start the task allocation. For example, the percentage of containers ready for use might be useful for this purpose. And this is a resource usage example of a certain slave node, in which, in this test, we lose the task locality in the start phase. So we found network usage, as shown in network usage graph. This increases the total process time, so you should prevent these cases. Okay. Finally, I talk about our future work and conclude this session. We have many future work, but I talk about two topics. We want to find a good collaboration between Spark and Yarn. And here are some issues to be resolved. For example, overhead for starting containers, and to avoid scale-up task allocation when starting applications. And secondly, we want to ensure traceability from a statement of application to the framework of Spark. This is very useful, I think, for performance tuning and debugging. Okay, I conclude this session. We have many expectations for Spark. First one is capability to scalably process tens of terabytes of data without unpredictable decrease of performance nor unexpected hold. We evaluated, and I think Spark is very good. But actually, we need some techniques for scale out. And secondly, we need a capability to keep reasonable performance when data is bigger than the total memory available for caching. Spark seems to be very good, but we need some technique to efficiently use the cache. And finally, capability to run an application on Yarn. We are evaluating now this point, and I think it is under a development right now and improving now. So I feel Spark is a young product and has some issues to be solved. But these issues should be resolved by the great community member, you, and we also contributed. Thank you.
I think we have time for one question, if there is a question. And in the meantime, can Veronica Ray prepare her slide? So is there a question?
Did you consider using Mesos instead of Yarn, or how did you evaluate that?
I'm sorry, one more please.
Did you consider using Mesos instead of Yarn, and how did you compare them?
I've not tried it yet, actually. I tried only Spark standalone mode and only Yarn mode. But because this is because we have already existing Hadoop systems, many Hadoop systems. So we want to correlate existing Hadoop with the Spark. So we chosen Yarn.
Cool. Let's thank the speaker.
Thank you.
Let's go. So next we have Josh from Bizo, who's going to present how they went from